Good afternoon, everybody. Welcome to our Virtual Connect series that continues this week with a special presentation in honor of Earth Day. We are going to learn about incorporating passive house design standards. Today's session is going to offer HSW credit, so we ask that you stick around for that for your continuing education transcript. We're going to explore the benefits of incorporating passive house sustainability principles and learn how passive house standards can be integrated with project processes and other green building goals. We have with us today a special guest. Our expert is Enrico Bonilauri, International Associate AI. Hi, Enrico. He holds 2 master's degrees, one in architecture from the University of Parma in Italy, and one in design science from the University of Sydney, Australia. As a registered Italian architect and certified passive house designer, he's worked in Australia, Europe, and North America. He specializes in building envelope design and analysis, informed by the thousands of hours spent on construction sites. His experience includes International Passive House Conference in Germany, Austria, China, and national passive house conferences in the US, Canada, Spain, Australia, and New Zealand. You've got a lot of stamps in your passport. He's co-founder of EMU and has been the scientific curator of its passive house curriculum, teaching American builders since 2017. Welcome, Enrico, and thanks for doing this. I know there's a lot to unpack here. If we took the full course, it would take a week. So we're going to get, I don't even think we can call it the appetizer. We're going to get just a morsel of what is involved here and hopefully stoke the curiosity for people to learn more. So Enrico, thanks for being with us today.
Thank you, Mike, and thank you, AAA, for having me. And thank you for everybody attending this presentation. I'm going to start sharing my screen now. And I think what's important to keep in mind is that our approach is from the point of the architects. EMU, our company, actually started back in 2008 as an architectural practice. And in falling down the rabbit hole of passive house and building science, we always try to make this information more readily available to mainstream via education by training, as well as helping manufacturers developing better products to be available and make it easier to improve the performance of buildings. Today I'm going to talk about how to incorporate passive house in the architectural practice and goals other than just energy efficiency. So these are the learning objectives of today. We're going to look at what the passive house building standards are and different implications as far as climate and nuances that you want to keep in mind in trying to optimize your project depending on the type of project you're working on for your climate and for the type of occupancy. We're also going to compare how passive house can be woven into the other green building goals and how it can be different from net zero and passive solar. And then how to integrate goals such as code compliance or carbon reduction to improve our building, and eventually evaluate how this impacts the process of different design practices depending on the type of building. So there's, especially working in Colorado, there's quite a bit of confusion between passive house, passive solar, and net zero. Passive solar is a movement started in the 70s that was trying to integrate more passive solar gains in the building by means of large extensions of glass and thermal mass. And more recently, net zero is a set of goals that allow you to offset the energy that your building consumes over a year. And if the energy that you produce over a year is greater to or equal to the one that you consume, then your building you can call your building net zero. What is important in this slide is that on the left, the 2 purple and yellow images represent the heat losses through the building envelope. And neither passive solar nor net zero really address how to improve the building thermal envelope. This is what the core of passive house is. We want to improve the quality of the building envelope considerably So then we can incorporate some passive solar gains as well as some renewables to achieve greater energy efficiency. But the real core is to having a considerably better built building. And in talking about passive house, you don't want to only think about houses. These standards apply to other building typologies than just homes. The image on the right-hand side shows the Cornell Tech building in New York that is a certified passive house building, which is a high-rise in New York. So it does not apply only to homes. So as architects, I think we would like to take a step back and ask ourselves, why do we build building? We have our lives and we want to enjoy lives with people that we care about. However, the weather has not always been fair. And so over thousands of years, mankind has invented buildings to protect ourselves from weather. Now, with our greater impact on the environment, we also want to protect ourselves from our own pollution. And the more extreme weather events and the more extreme conditions become, the more we need this kind of protection. Last year was particularly sensitive as far as wildfires. We're going to see today some data as far as indoor air quality in event of wildfires and how we can improve that, as well as there are conditions now that force us to stay inside the buildings. And so really our interior environment represents where we spend most of our lives. So why buildings? We want to provide ourselves and the people we live with environments that we can control in terms of comfort and in terms of quality of living. So this is back to the big question, why? Why do we have buildings? And this is very tied into the concept of passive house. Passive house really puts the envelope first. This diagram in the center shows the 5 cornerstones of passive house we're going to cover in a second. But at the end of the day, we want to create an environment that we can control in terms of thermal comfort and indoor air quality. And on the right-hand side at the top, that is an infrared image showing on the right-hand side a coffee pot, just a regular glass coffee pot that it is supplied with heat constantly in order to remain warm. And it is warm because you see purple in the infrared image. And if the fact that you can see purple means that coffee pot has a lot of heat losses. And the moment you unplug it, you start losing heat considerably. And that coffee pot does not remain warm for a long time. Whereas on the left-hand side, you see a thermos that has much lower temperatures on the surface because there's not as many heat losses. We're going to see later today in this presentation how the passive house building envelope is just that. It is the thermos that we can control, and we have very durable conditions even if the power goes out. Now, the cornerstones of this thermal protection include thermal insulation and thermal mass, abundance of thermal bridging, quality of windows and doors, as well as we achieve high indoor quality by means of a combination of air tightness and continuous filtered fresh air. So these are the cornerstones of the passive house concept. The practical implementation on specific projects depends on climate in the first place. The colder the climate, the more thermal protection you need, as well as the type of occupancy. If we're talking schools versus factories versus residential buildings, there are significant differences in how we achieve this quality. So starting from thermal insulation and thermal mass, thermal insulation, I hope everybody knows what it is a range of materials that slow down the heat flow through an assembly. And thinking about Climate Zone 5, that is Denver, for a single family house, you're looking at R40 to R50 walls, as opposed to R20, that is the code minimum. But if you're looking at larger projects, like multi-family larger buildings, that R value drops to R30, maybe R35. That is a combination of form factor as well as type of occupancy, which we're going to cover later today. Now, the other side of this is thermal mass, shown here as concrete. But if you're concerned about carbon, there are some very good products that allow you to incorporate thermal mass in your buildings that are not as carbon intensive. Now, the misunderstanding of thermal mass is that Thermal mass is very good at buffering very high gains. So if I have a lot of sun, or if I have very high internal gains, having thermal mass does allow to use that. But that is often overrated for residential buildings, and it's often underrated for commercial buildings. So in this graph here, you see the typical distribution of internal gains in a house. That is the orange line at the very bottom that is almost constant throughout the 24 hours of the day, versus the brown line that represents a classroom where it's empty for most of the day, and then you have very high occupancy for while the school is open. So that is why thermal masses, for example, is underrated for school buildings, for example, because it really can improve the utilization of these high interior gains. And you can get to passive house without really having any significant thermal mass in your building, just a very good amount of thermal insulation. Thermal bridging are weak areas of said thermal insulation caused by poor design or poor installation. The result is shown on the picture on the left. That is a photo from Fort Collins, where especially in the dark areas of the stucco is covered by with frost, but the vertical and horizontal streaks that you see, those are areas with higher heat losses caused by thermal bridging. And that is clearly a sign of poor quality design before even construction. Now, thermal bridging have two main consequences. The more impactful of the two is the risk of mold condensation, shown in at the bottom right side of the slide. The fact that they have high heat losses means that they have localized areas of the internal surfaces of my building where the temperature is lower. And with lower localized temperature, that is the breeding ground for mold and or condensation, which can significantly undermine the indoor air quality inside the building. Now, the way we address this is analytical. There are software that are used for that, and we can talk about those in the Q&A session afterwards. But you're basically looking at two values, two KPIs. One is the temperature factor FRSI value that allows to address risk for mold and condensation on the surfaces. And the second one is the psi value for linear thermal bridges and chi value for point thermal bridges. And that allows you to better calibrate an energy model and avoid performance gap between the design performance and the way the building actually performs once it is occupied. We're going to come back to the performance gap later today. This is an example from a project in Colorado where you are standing on the inside of the building looking to the outside at an exterior wall, and you see a couple of things. You see a lot of timber, a lot of studs grouped together, and you see a metal beam. Now, in addressing thermal bridges, you want to see which ones you need to address and spend money and time against versus the ones that you can live with and not mitigate. In the class that we teach, we call the ones that you have to address, we call the elephants. And in this case, the elephant in the room is the metal beam. The 3D thermal bridge on the right-hand side shows that it just goes out that the FRSI value is too low, meaning that there will be mold or condensation forming there. Whereas the ones that is a mouse you're looking at the floor plan view of the wall assembly. And although there's a significant amount of wood reducing the R value around the wood column, the FRSI value is actually okay. So as a design, you can decide not to address this kind of thermal bridge because it will only impact the energy performance, but overall the building may be okay. Again, the determining factor, in my opinion, is to avoid mold and condensation as a first priority. With no net zero or green building is efficient or green if the indoor environment is not healthy. So avoiding mold and condensation needs to be a very high priority for everyone. In addressing thermal bridges, you want to look at your floor plan sections and details and spot any metal, concrete, or masonry because those are immediate red flags. Whereas timber is not necessarily a red flags for mold condensation as well as loss of performance. Red flags means that as little a piece of metal as a metal flashing needs to be addressed, because that could cause significant thermal bridging if it goes through and cuts through a layer of insulation. I'm gonna try to speed up a little bit. There are different failures associated with windows and doors, including condensation, ice, mold, thermal discomfort, and air leakage. And none of these are suitable for a passive house. There's actually a few criteria that windows and doors are required to be met in order for the building to be called a passive house. And you want to ask yourself, other than passive house goal, is any of these failures suitable and good for any type of building? Like if I have condensation and ice, is that good for the building? Because code still allows you to have this kind of damages. We're going to see that today. In fact, NFRC, until a couple of years ago, had the condensation resistance, which is highlighted in the bottom left label with the number 51 in that case. And that does not really address much. It's only used as a way to compare different products, but it does not really address an actual actionable item to avoid condensation. They are now moving to a condensation index, which is getting closer to the way passive house approaches things, but it's not there yet. Passive house uses the temperature factors that I covered earlier, and those apply to all parts of the building in order to avoid mold and condensation throughout the building. And on the thermal comfort side, passive house has a very proactive approach in that if you look at code, if you look at the U value or U factors for windows and doors, those that were declared in the IECC, they are driven by trying to improve the energy efficiency of building. And they very, very slowly improve from one issue of code to the next. But if you look at the orange numbers at the center of the slide at the bottom, you can have very cold temperatures caused and driven by the U values, the IECC U values not being good enough for the climate. Whereas the requirement for passive house for windows and doors is you need to have thermal comfort. And thermal comfort means you have to have, in this case, 62.4 degrees as an average temperature on the inside of your window and door in order to have thermal comfort. And that design temperature drives the maximum allowed U value for windows and doors for passive house, shown on the right-hand side of the slide. So in other words, code has a reactive approach to thermal comfort, whereas passive house has a proactive approach, meaning that comfort drives performance. And on a practical level, this translates to different products being used in different climates. Starting from number 2 in the center of the slide, Denver, Colorado, we're looking at triple pane glass for thermal comfort, and typically a passive house B-grade window. Not all triple pane glass windows are suitable for passive house, and not everywhere in the country you need triple pane glass to mean passive house. This is something that we may investigate a little bit at the Q&A. But long story short, you can see with the number 1 at the bottom right, project in Georgia, we're using an uninsulated UPVC frame with double pane glass, and that means passive house certification because the climate is mild and the performance is, you need as much thermal protection as the harsher and colder the climate is. In fact, the third image in this called out in number 3, that is Jackson, Wyoming, that is climate zone 7. And that is where we need to have better windows and better glass to meet the same comfort criteria. When it comes to indoor air quality, there's a myth about buildings needing to breathe through the skin. And if you think of the largest animal that can breathe through the skin is a little salamander, which is represented here in the slide. And little salamanders don't live year-round outside in Colorado, for example. Nor they have good control over the quality of the air they breathe. These 2 graphs in the center of the slide show indoor air quality monitoring that I executed in Nevada a couple of years ago. One at the top shows opening the windows in the morning to get some fresh air through. Temperature, which is the red line, drops, so you do get cooler in, but you also get pollution, that is the green and orange lines, that is particulate matter 2.5 and 10. And at the bottom of the slide, you see the same monitoring in case of pollution coming from the inside, that is from cooking. And that is, if you don't have an exhaust in your kitchen, you just rely on window ventilation, then you're compromising the quality of the air by just having to open the doors and exposing yourself to the quality of the air on the outside. So if you think of the human body, we do have a dedicated mechanical ventilation system, and that is what we use in passive house, with the main purpose is to supply the building with filtered fresh air in order to maintain high indoor air quality. This is an example of a indoor air quality monitoring from Australia. The picture is actually from me hiking last summer, and that was brutal wildfire smoke that we had near Berthold Pass. And so, this is something that is becoming more and more common to have times of the year where the outdoor quality of the air is just so low that you cannot rely on that to provide indoor air quality. This study executed by Cameron Monroe near Melbourne, Australia, shows how the combination of building air tightness and filtered continuous ventilation allows you to control penetration of pollution from the outside in. They had similar cases of wildfires, and the outdoor pollution is represented by the blue line in this 3-day monitoring. The red line shows a regular passive house with a regular F7 filter. But if you swap the F7 filter with a HEPA filter, then you have much better conditions and you stay underneath the threshold requirement. So long story short, the combination of air tightness and mechanical ventilation does provide the building with better energy efficiency, but the main goal is to actually provide control over the indoor air quality. That is, air tightness keeps any pollution out, and then you filter whatever comes in. Building up on the complexity, these systems are actually fairly simple, but it does require integrated design. Because the selection of, the more the buildings become airtight, and this is aside from passive, the more buildings become airtight, the more the different components become interrelated from one another. And so a poor selection on a window product or a poor selection on a ventilation strategy may affect the other component or the other way around. So as architects, we may want to start looking at what's the temperature factor on windows and what is the ventilation strategy. The reason I cover this is because in very cold climates, code still allows you to have intermittent ventilation, and that allows for considerable moisture buildup in terms of relative humidity inside the building, which leads to condensation. So the ventilation strategy needs to be addressed in combination with the type of building components, windows and doors, for example, that we select, because intermittent ventilation will probably result in condensation of windows. And that is that the mechanical engineer fault or the architect's fault? Is probably both. So just the more the building become airtight, the more these issues are going to become more and more common. As it is more common to have building failure due to lack of air tightness, the picture on the right shows a roof that was poorly designed and exfiltration caused the building to fail and to rot. So if you want to remember one thing about why we're building buildings airtight, is to allow for more durability as well as more control over the indoor air quality. I don't want to dive too much into this today, but I'm happy to answer questions later in the Q&A session. This is something that is very interesting because it's the proof of concept of the passive survivability of the thermos, that is the passive house thermal envelope. On the right-hand side, you see the same infrared image that we saw earlier with the thermos having fewer heat losses, and so it is now it does not shine as much as the coffee pot on the right-hand side. These images from the workshop that you see at the bottom, that is the builder training that we have in Nevada, where we teach builders how to implement passive house in terms of insulating better, air sealing better, and we have them practice on the mock-ups that are represented being assembled on the left and being completed and exposed to the outside and the snow on the far right-hand side of the slide. These are fully enclosed micro buildings that we heat up and then for a certain amount of time, and then we carry them outside in the cold to let them cool down, and whichever remains the warm the longest wins, because they have achieved the highest thermal resiliency by means of building better. What is interesting is that we also have a baseline pod that is built according to the 2018 IECC code. And time again, we see how the code pod gets colder much quicker. And in the case of the slide, in the graph in the center of the slide, after 13 hours of being exposed to the outside, it was a good 20 degrees colder than the average of the passive pod. So this is showing how implementing a better strategy for your building envelope allows a better passive survivability of the building in case power goes out. Buildings remain more comfortable and not as dependent on power in case of extreme weather events. So talking about passive house standards, we use the plural because there's a couple of them. They are all based on the principle of conservation before compensation. You build better, you have less demand for heating and cooling, you need less energy in general, source energy or site energy, you have better air tightness, have greater indoor air quality, and have thermal comfort and avoidance of mold and condensation. All of these are criteria that build up the standards for certification. Now, there are two institutes that provide this certification. One is the International Passive House Institute, and the other one is the Passive House Institute US. They used to work together. They don't at the time, which I hope they will work again in the future, but not at this time. The International Passive House Institute at the top has three main protocols. Passive house at the very top applies to new construction as well as retrofits. The low energy building is kind of an intermediate step for new construction only. And Enrofit is a protocol that is specifically designed for building retrofits. Whereas the Passive House Institute has the Fuse Plus protocol, which applies to both retrofits and new construction. Comparing apples to apples, you see on this graph the maximum allowed heating and cooling demand for the International Passive House, the Fuse Passive House, the low energy building, and the Enrofit. Clearly, the lower the column, the more strict the standard and the more efficient the building. And on the right-hand side here, you see the maximum allowed air leakage at the blower door test, with the International Passive House at 0.6, Fuse 1.3, low energy building at 1. And keep in mind the code is at 3 ACH 50. So all of these are significantly more airtight than cold buildings. Compared to existing buildings, implementing the Enrofit or the Fuse standard allows typically an 80% reduction in heating, whereas the International Passive House is about 90%. And compared to new construction complying with the 2018 energy code, the low energy building and Fuse allow for about 60% reduction for heating, whereas the International Passive House is about 80% reduction in the need for heating. So if you're looking at trying to get to net zero or significantly reduce your need for energy, these standards allow for a very good tool to get very far in that reduction, whether you're looking at retrofitting a building or having an improvement compared to just a baseline of code compliance. Something that is very important, the closer you get to zero energy consumption, the more everything matters. So the design tools need to be more accurate, the implementation needs to be more accurate, you just need to be more thorough. And this leads to performance gaps sometimes. That can be performance that can be caused by just using prescriptive paths or having simulation softwares that are not very accurate, or design that is not very detailed, or construction that is not very thorough. So Passive House is very OCD, if you want, about the whole process, and that leads to a performance gap that is negligible. That is shown on the two graphs on the right-hand side. The top is from the UK and the bottom is from Germany, but it shows very good correspondence between the design performance, the expected performance, and the performance as the building was occupied. Whereas the graph on the left about LEED shows that for the gold platinum, especially, the energy usage can be significantly higher than expected. Does it cost more? Kind of depends on the type of building. Single-family homes typically cost more just because of the form factor. Passive House is about the envelope, and so per square foot of treated floor area, you have more square feet of building envelope in smaller buildings. We're going to see in a minute what it means. But larger projects, you can get to cost parity as long as you have integrated design. Meaning that you invest more on the envelope, and this typically allows for significant savings as far as the mechanical systems. There are some considerations as far as user experience and zoning and whatnot, so you may not capitalize on all the savings that you may get, but you can get to cost parity, especially in mild climate zones such as climate zone 5 and 4, whereas colder climate zone, it may still be difficult to get to cost parity with code. And at the end of the day, you need to get to cost effectiveness, just like any goal, you need to understand the programming, have clear goals, and have integrated design. We had issues with MEP engineers not believing the very low loads that you have in Passive House buildings, especially in buildings such as schools and offices. And so they were unwilling to downsize their mechanical system. And so we did not really benefit from that economy. There was no cost reduction there. So it was only the extra cost for the building envelope. So that kind of integrated approach and teamwork is needed to have cost effectiveness. This is an example from a school, a case study in New York City, where they decided to implement Passive House, and the extra cost over the baseline landed about between 2 and 3% of the cost of construction. So this, with decent amount of work and integration, you can have the kind of comparability with code. But that, in this case, they were extremely thorough as far as integrated design and seeing exactly what they needed. So this is a good example of how you can significantly reduce the extra cost by having good integrated design. Getting to Passive House through a project is a process. I intentionally looked at pictures of sailors looking for land, and you start using the spyglass, and then you get to the magnifying glass, and you look at the microscope. Now, something that is a little bit difficult of the Passive House approach is that sometimes you need to look at the microscope, even if you are very early in the stage. And so there are a couple of steps that may be a bit tricky if it is the first time that you're going about it. But it is, the good thing is that once you learn these steps, it becomes a second nature, and you never go back. Early design integration, this comes from the architecture 2030, and the sooner you get on board, the more significant changes you can make at the lowest cost. The good news is that there's a couple of tools available now to help visualize and integrate the design process early on. The big picture at the bottom right is a plugin for SketchUp that allows to study orientation, massing, shading while you're still at the very early design. And there's also plugins for Revit and ArchiCAD, which I don't have a direct experience with, but these tools are becoming more and more available, because at the end of the day, whoever the energy consultant may be, us architects have a very, very strong impact on what is how the building is going to perform down the line. We have an impact on the form factor, on the orientation, the distribution of glass, which the most difficult thing that we do as passive house consultants is when we receive a drawing set and the architect says, make it passive. And when we are at DD or CD, that we're never going to get to passive house if we get so late in the game. We do want to get in early because there are significant changes that can be implemented and can benefit not only the performance, but also reducing budget, reducing the cost, while producing a better building. So as any strong goals, and passive house is definitely a strong goal for the design, the sooner this is built into the program, the better. Form factor is something that is significant, and it's just about geometry. Top right, we see a demonstration unit, basically a tiny house, which is tiny. It has about 300 square feet of treated floor area, so very small. And we have a single family house and we have larger commercial buildings. And if you look at the form factor is the amount of square feet we have per square foot of treated floor area. So the envelope is where passive house is expensive. If you have fewer square feet of envelope per square foot of building, it's going to be cheaper. And so this is why larger buildings are per se cheaper per square foot to get to passive house, just because you have fewer square feet of building envelope. In fact, if you look at the comparison between a single family house where the form factor is about 3.5, commercial buildings, that is not 3, that is like 1 or 0.5, so significantly fewer square feet of building envelope, so cost per square feet of building. This is just geometry. And so the higher the form factor, the more expensive it is and the more difficult it is to achieve efficiency. Whereas the low form factor, it's cheaper in general to build. It is easier to achieve the efficiency. So as architects, if we can simplify the form of just the building envelope and then create intrigue with other components of the building, that is how we can significantly contribute to making buildings more efficient. Crosswalk with other green building standards. LEED version 4 does recognize passive house as an improvement in energy efficiency. Living Building Challenge doesn't recognize passive house, as well as the Carbon Leadership Forum. There's not a recognition yet that I know of. But the good news is that passive house is all performance based. And so in terms of how you decide to build your building, you can use some very carbon intensive as well as some very carbon neutral or carbon negative assemblies. That is up to you. And you can get to passive house either way. So if you're looking at low embodied carbon, that is definitely something you can build into passive house very organically. Compliance by means of passive house. The software that we use is called PHPP, Passive House Planning Package, which is a whole building energy modeling, and it's based on building science as well as decades, literally, of data collection from occupied buildings. And it is developed by the International Passive House Institute. It is validated according to ASHRAE standard 140, and there are more and more municipalities in Colorado that accept the PHPP calculation to be submitted in lieu of manual J. So you don't have to redo the work multiple times. You can just submit PHPP. The Passive House Institute US uses WUFI Passive, which is based on the same type of calculation as PHPP, and it is developed in Germany by the Fraunhofer Institute, and then it is used in the US by the Passive House Institute US. City of Denver has some net zero goals, and I had a look at those. The good thing is that they invest on performance-based, and they are looking at buildings that are performing as designed and eliminating trade-outs. Something that is also positive is that they want to address public health in terms of protecting from outdoor pollutants and indoor pollutants, including gas cooking. The one thing I think is weak, and I'm in conversation with City of Denver, is that, in my experience, neither IECC nor NFRC yet address the issue with molding condensation properly. And that's something that I think needs to be amended in code, because the more buildings become airtight, the more risky is going to be, or the more risky it is, because that is the reality we work with today. The Denver Net Zero Green Building Code does include some considerations for passive house. And so if you're interested, this is something that can be valuable to be looked into. Some examples from around the world about residential passive house buildings. We have some houses, we have some high rises and mixed developments from Europe, the US, and China on the right-hand side. Commercial passive house buildings from different climate zones, including colder climates such as Germany, or very warm climate such as Dubai, top left of the slide. And some of my favorite passive house building is the museum in Ravensburg at the bottom left. That's a very beautiful building, and it is also a passive house. So you can actually do some very nice architecture by just having a much better building envelope, and just adding that to what you do as an architect. And because this also applies to energy retrofits, these are just some examples from retrofits. Left is from Germany, middle is from Brooklyn, New York, and on the right-hand side is from Canada. So to recap, passive house is based on the envelope first, which allows for more resilient and durable buildings in general. At the end of the day, the building envelope has significantly lower complexity than mechanical system. There's no moving parts other than windows and doors in the building envelope. And that allows for just longer durability of those components over mechanicals. So passive house also has a very thorough approach towards comfort, condensation avoidance, and proper ventilation, which are in favor of putting people at the center of why we're doing buildings. This is extremely important in an age where it seems to be attractive to turn buildings into small power plants. I think us as architects want to keep in mind that why we're building buildings, and I think buildings should be designed around people. Passive house becomes a very streamlined path to net zero because you significantly reduce the need for energy needed for heating and cooling. And it can also be a pathway to code compliance and a crosswalk for other sustainability protocols. Architects, we can contribute significantly to achieving efficiency in general and meeting passive house goals, just keeping in mind what the goals are and implementing those tools at the early design stages. And finally, the earlier these kind of goals are set in the program of the project, the sooner the better, because that is how you can bring everybody on board and have an integrated design approach. That being said, this concludes my presentation, and I'm happy to answer questions.
Thanks, Enrico. That was fascinating, and you had to cover a lot of information in a short amount of time. So I'm sure there's going to be some questions. And
very fast.
Yeah. So we've got some more time remaining, which is great because we're going to have some questions for you. The first one that's come in, Chris asked, what are the savings in building operations costs when implementing passive house?
It depends on the climate and on the type of building. With regard to heating, even compared to a brand new building complying with the 2018 code, you can cut the need for heating by 80% for a single family home. If you're looking at schools or commercial buildings, it may be significantly different. So it kind of depends on a project by project case.
Kylie asks, is form factor still a good metric for massing comparisons of high-rise buildings?
I would say so, yes. And that applies not only to heating-dominated climates, but also for cooling-dominated climates. So typically, the more compact the building, the better, because if you want to control your building, the less surface exchange you have with the outside environment, the easier it is to control. So that is where us architects just messing. It's a very powerful way. One thing that you cannot fight is geometry. Geometry always wins. And so that's the truth of what we do.
Yeah, there's no fake news in math.
Yeah, exactly.
It's sort of a related question, and you talked about red flags earlier in the presentation. Karen asked, does passive house work better with certain building types or material selections like wood frame, masonry, with SIP panels?
So you can achieve passive house with any construction system. Clearly, if you have a steel frame, think of steel is very good at conducting heat. So or concrete, so if you have a lot of steel, if it is a steel frame building, you're going to end up having a lot of continuous insulation, so that if you want to have that stat cavity with steel frame insulated, you can assume that half of that R value is gone just because of steel frame, but you can still get there. Timber framing works very nicely. SIPs works very nicely, but there's no constraints really as what you can do. And my experience is that maybe that's because we teach builders, but if you get on board with what is most commonly used locally, that is going to be the easiest, because physics is simpler than convincing subs on site to do to doing the right thing. It's easier to adjust passive house to a construction system than teaching subs on site to doing something different that they're not familiar with. So in the bigger strategy of a project, trying to get passive house to passive house by means of whatever is the easiest and most commonly used locally is the best strategy, in my opinion.
Yeah, what that labor force is used to doing on a regular basis is going to be faster and cheaper than trying to introduce them to a whole new technique.
Correct. Yeah. So that is where the human component comes into play. Somebody needs to put this together.
Yeah. And it's great that you do training for those builders, and not far away either. So that's cool.
Yeah, it's something. It's very enriching. We get a lot of questions, and there's a lot of smart people that come by. So it's kind of a privilege to have access to that kind of pool of people, because there's a lot of smart people out there.
Are builders becoming more interested in this?
Definitely so. There is one of the main reasons why builders come to us is because they know that just code compliance does not really protect them in terms of moisture management in buildings. And so we get a lot of people come to take the training because they want to know more about ventilation or about how to avoid condensation. So we get a significant amount of builders coming through, and energy savings is secondary. Main driver is health comfort, managing moisture properly. So kind of the bigger picture value that passive house can provide, other than just energy savings.
So on the builder side, there's different drivers and motivations. What about on the client side? There's always going to be a certain subset of the clientele that comes to a designer with the desire for passive house. But what if you have that which you want to bring to a project and you want to convince a client to do it? What's been the arguments that have worked, and what have been some of the challenges? Stephanie's asking this question.
So
convincing clients to adopt passive approaches.
So Windows provide a perfect example. You get a brand new window for Clemson 5. It has a 0.3 U value, which, if you look at Denver, means that on a cold day you can get as low as 50 degrees on the inside of your window. Whereas for the passive house, you get at least 63 or 64. And homeowners or clients don't understand U values, don't understand energy, but they understand 50 degrees is cold and 64 is fine. So thermal comfort is a big one, as well as indoor air quality. So those two are huge drivers. And then certification is something that it's pretty thorough. It's not as bureaucratic as LEED, in my opinion. But it is a way to keep everybody on track and have a clear goal, because the moment you remove certification, then everything becomes fuzzy and undetermined. So it's just like removing specs from a project. It becomes, whatever, comes by.
Yeah. David asks, are there Denver new house case studies available?
We have a few being built right now, so stay tuned.
Great. And Dylan wonders, have you looked into the comparison between the PHI and the PHI US Plus 2021?
I have not looked at the 2021 yet. So I put together these graphs based off of the Fuse PHI US website.
Okay.
And build that comparison. I think the 2021 is in beta still. I don't know. I don't think it is being implemented yet. So today you're still working with the 2018, I think.
Okay, so that bar graph where you're showing the 80% for PHI and the 60 for US, that was based on the current standard, not the 21.
Correct. Yeah, I think it said at the bottom the 2018 plus.
Okay.
Yeah.
Can you address, from Karen again, controlling ventilation versus freedom to have open windows as desired?
Yes.
She says she noticed the house in France that you featured had a lot of openings.
Yeah, so unknown to most people, it is a specific requirement in passive house to have at least one operable window per room of prolonged occupancy, bedroom, offices, whatever. And that is just for the psychological comfort of being able to open something. On the air quality side, the mechanical ventilation allows you to have filtered fresh air where you need it, when you need it, and continuous. Whereas opening the windows, you give up on that control. So if you live in a city, or if there's concern for pollution outside, you are giving up the control of filtering whatever comes in. So it is possible to open windows in a passive house. The graph that I showed from Australia actually showed that in case of opening the windows, the outside air was poor because of wildfire, and so by opening the windows, you were letting pollution in. So
Where that spike came in. Yeah.
Yeah. So it is.
Doesn't matter what kind of filter you've got.
What's that?
Doesn't matter what kind of filter you got on your system at that point.
Exactly. So occupants of passive house project that we have executed and have been occupied for years, they open the windows like a few times per year. They are fully operable, but they have fresh air continuously to the ventilation system, and so that need goes away. The need for fresh air, the fresh air is there because the ventilation system supplies that continuously.
Okay. John Paul says he's traveled to Australia, Japan, and Europe, and is jealous of your how well traveled you are. Are one of these locations better for this building approach than others?
In terms of climate,
or policy, or adoption and acceptance levels.
So starting from the climate, some climates are easier than others. Colorado is super easy because it is sunny and dry, and from a building science point of view, it is one of the easiest climates that there is. What is difficult at elevation in Colorado is we get some very cold temperatures, which only few products in terms of windows and doors can meet the comfort criteria. And that ties to product availability. Now, even just compared to a few years ago, there's now a good number. There are dozens of products available in the US that are suitable for passive house in terms of windows and doors, for example. So compared to just 2016, 2017, the market has completely changed in the US. That is driven by demand. Demand in the US is very much pocket specific. New England, New York, Pennsylvania, Pacific Northwest are the pockets with biggest demand for passive house. Other than, Vancouver is very big. And cities like Vancouver and New York have streamlined the path for permit approval, as well as I think Pennsylvania has some grants available for passive house projects. So by pocket in the US, there's quite a bit of development. We're seeing a lot of interest in Colorado in general, even in the past few years for passive house projects. So that demand is definitely growing here as well.
We had, I think, featured in our last newsletter for members, the Denver initiative you talked about, where they're still accepting pilot project applications for those 5 demonstrations. So be nice to see a passive house one on that list.
Yeah, I think there is. And also other cities, we have some informal conversation with some code officials that are interested in looking more into passive house modeling. And if you go down passive house, then you don't have to redo your manual J, or you show compliance with net zero goals that the city may have. So I think there's a lot of people that are very open toward this in Colorado. There's just not a ton of projects yet, but there's a good number being built right now.
Yeah, and as benchmarking ordinances become more common, it's going to be a real easy way to show your energy use intensity decreasing.
Yeah.
You mentioned the market changing. Are there very many sources available for triple pane residential windows, if that's what's going to be part of the envelope?
There are, locally manufactured. There's Alpen in Louisville, Colorado. There's a wood frame manufacturer in Colby, Kansas called Advantage Woodwork. And those are some very good windows in terms of design and quality. But yeah, all these options were just not there back in 2015, so there's definitely options that are made in Kansas or Colorado, so market is catching up.
Yeah, and the other markets have been doing that for quite a while, in Europe, for example. So
yeah, there's also quite a few that import windows from Europe. Yeah, there's a lot of options available.
So a couple of questions just to bring us home. What types of buildings make good retrofit candidates? So if you're thinking of, if you're working with a client or just observing in your community different building types, what would be a good candidate for that? Because I imagine it would have a lot to do with the style or the structure that's already there. Well,
yeah, and that is taking a step back is what makes a good candidate for retrofit in general. Is the structural sound and worth keeping? Is the building of value from a landmark point of view? This is prior to any passive house consideration. What is important is that you can apply this to passive house, and even if you don't get to the full passive house, you can get to the end of it, or you can just implement the best practice and have a very comfortable building. But you can reduce the need for heating and cooling by 95% compared to the existing structure. So it comes down to clearly the larger the building, the easier. That is, fewer envelope square feet per, it's geometry again.
Yeah.
And then if the structure is sound and it's worth keeping, then it's probably worth looking into passive house. If the structure is rotted and unsound, and like if you're spending more money to fix it and build it a new one, and there's no historic value, then is it worthwhile keeping it? Those are the bigger picture considerations that apply to any kind of retrofit, regardless of passive house.
Oh, we had a follow-up from Mariana about the windows. I'm going to put that in the chat real quick. There just happens to be a demonstration at Alpen this Friday, so if you want to check that out as an attendee. And then one last question, which is for those who are curious about learning more. Obviously, we just scratched the surface here. So is there, if someone wants to get more information or to find training, or if they don't have the training themselves and they want to connect with somebody who already has all this training, let us know what some next steps are.
So the training that we provide, it is called for passive house builder training, but we have a lot of architects taking it because it's very good for architects to have this kind of knowledge, and then it kind of we need to decide what we want to be in life. Like EMU, my company, used to be an architectural practice, and then we fell down the rabbit hole of passive house, and eventually we moved away from practicing architecture. We don't do that anymore, so we fell so deep into the rabbit hole that we just teach and consult on this. And so in looking at this from an architecture point of view, the next steps, there are some resources online. I just don't have the links. Okay, so I think Mariana posted our website on the chat. There's also some videos or presentations that I gave about windows or ventilation systems that are more specific, and I can dig them up if you think that's a good idea.
Yeah, we'll have our editorial committee has someone on the call to capture this. And so we'll do a recap article that'll appear on our website. If you want to get those resources and links to me, we'll make sure it appears there.
Yeah, there's plenty of information out there that is great for if you're just considering, if you're looking at this as a career change or just integrating that in your practice. This is the time to do it. This is not the future, this is today.
Yeah. Well, this was super informative, and I really appreciate having an international resource, to be honest with you, right here in our own backyard in Colorado. So Enrico, we really appreciate all you're doing to advance the building science and the overall acceptance of environmental stewardship that Passive House provides. So appreciate you very much. Thanks.
Thank you. I appreciate being part of AIA Code Committee.
Yeah, and on that note, I was going to mention, that Enrico is one of 17 AIA Colorado members serving on our Committee on the Environment this year. So if you'd like to know more about what they're up to, you can contact our office. Nick Remus is the staff liaison for that. And as we wrap up this one, I want to let you know about a couple other things coming up in the near future. We have the evolution of custom glazing next week on April 28th, another HSW credit offered by Studio NYL. And coming up very soon is the awards program call for entries, which will be announced on May 5th. So we hope to see your best work in those call for nominations and to see you again soon. Thanks. Have a great rest of the week.
Thank you.